Okay, OChem 2 students, wrapping up this worksheet at the end of alcohols and epoxide synthesis. In class, we showed the solution to these two problems. Here we see selective reduction. I need to reduce a ketone to an alcohol without reducing the ester to two alcohols. So we saw that this required the more mild reducing agent, sodium borohydride. What we saw in the other direction is that the strong reducing agent will reduce the ketone to a secondary alcohol, and it reduces the ester into two alcohols. In this case, both primary, but every carbonyl of an ester will always give you a primary alcohol, and the ester linkage of an ester will be some variable, methyl, primary, secondary, tertiary. The other problem here was the opposite. Rather than synthesizing alcohols via reduction of carbonyls, here we're reacting with alcohols by creating carbonyls, reacting with alcohols to create carbonyls. Going upwards, we see that our secondary alcohol is turned into a ketone while the other secondary alcohol remains unchanged. So what's different between these two secondary alcohols? One of them is benzylic. It's located just off of the ring. The other alcohol is not benzylic. In a selective oxidation, where only the benzylic positions are oxidized, we need our selective oxidizer, MnO2. Whereas if we used PCC, and in fact if we also used chromic acid, we'd get the exact same result here. Careful not to run it too high or too long that we risk benzylic oxidation. PCC takes both of those alcohols and turns them into ketones. On the backhand side, the majority of this worksheet, we see multi-step synthesis. Remember in multi-step synthesis, to map your carbons, that means not just counting them, but showing where they appear between starting material and product. Brainstorm, what reactions do you think you can use? What intermediates might be present in your reactions? And lastly, work forward and backwards. Don't just take the starting material and try to figure out how it can be changed into something else, but look at the product and consider how you can make the product from something else. Remember that this section is going to include OChem 1 reactions, benzylic reactions from section 16, EAS and NAS from section 16, and now also the reviewed reactions to make alcohols, reviewed reactions with alcohols, as well as new reactions to make alcohols, new reactions with alcohols, and reactions that make ethers and epoxides, reactions that use ethers and epoxides. Like we said in class, ethers are fairly inert, so epoxides are much more common here. In my first problem, I see a halohydrin starting material. This stands out to me because in this vicinal position, I have both an alcohol and a halogen, and they have anti-addition stereochemistry. The alcohol is wedged, the halogen is dashed. Halohydrins are a good precursor to epoxides. We saw this in our synthesis of epoxides in class. So I have a feeling there might be an epoxide in this synthesis. We'll see if that holds any weight. I also see in my product that I add this nitrile group and that I have an alcohol as well. And there's some interesting things about stereochemistry. The alcohol is now on a different carbon, but it has the same stereochemistry. I can see that this methyl carbon has stayed in the same position, so it's my alcohol that's moving, but the methyl has changed its stereochemistry as well. Mapping your carbons here, we can say here's positions 1, 2, and 3, methyl, tertiary alcohol, halogen. Here's positions 1, 2, and 3, where we see that the alcohol has truly changed positions between 2 and 3. Well, how can I add a cyano group while also having my alcohol move around? Although we didn't see this in class, we hinted at it, and you should see this in your homework as well. Cyanide as a nucleophile can run acyl addition on carbonyls. That means that cyanide can create this cyanohydrin product at the same carbon position. That's not what we see here. We don't see cyanide binding to the same carbon as the alcohol, which means we're not looking at acyl addition. In terms of brainstorming, this is actually a reaction I can throw out for this problem. Okay, so let's see if I can work forward and backwards for this problem. To work forwards, I'm going to try and create an epoxide. I'm going to add NaH, which deprotonates my alcohol, turns the alcohol into a strong nucleophile, and creates an epoxide like this. Now from my epoxide, I want to open the epoxide, and I want to place the alcohol on the less substituted carbon, and I want my nucleophile, the nitrile, to attack at the more substituted carbon. We saw yesterday in class that in acidic conditions, a nucleophile will open from the more substituted position, whereas in basic conditions, the nucleophile will open from less substituted positions. Steric strain and a negative charge push the nucleophile to the less substituted position here, whereas positive charge stability pushes the nucleophile to attack more substituted here. I want this to open at the more substituted position. If I want my epoxide to open at the more substituted, I need this to be acidic. I need it to have positive charge character. So I'm not going to introduce Cn as my reagent. I'm going to introduce HCN. HCN is hydrogen cyanide, and this creates an acidic condition that protonates my epoxide. When my epoxide is protonated, it's easier then for the nucleophile to attack at the more substituted position. Notice how this epoxide preserved the stereochemistry of the alcohol, and now by being attacked at the more substituted position, the alcohol still retains its original stereochemistry, wedged, although now it's bonded to a different carbon. In this two-step synthesis, we've taken our alcohol from one carbon to the other, keeping it on the same face of the ring the whole time. Okay, why don't you pause and consider how you might solve this next synthesis. The first step here should be counting your carbons. I'll call my benzene ring position 1. Then I get positions 2, 3 coming off of the benzene ring. And as I look in the product, I can see that I need to add this group, carbons 4 and 5. I need to make a carbon-carbon bond. So as I'm brainstorming for this problem, I'm considering a Grignard reaction. Grignards are good at making carbon-carbon bonds. As I consider making a Grignard, I have a lot of ways that I can use Grignards. For instance, Grignards can be used in acyl addition, similar to the cyanide, but that would create a carbon-carbon bond at the alcohol carbon. I can see in this problem, the alcohol carbon, carbon 2, is not creating a new carbon-carbon bond. Instead, it's position 3 that is creating the carbon-carbon bond, while carbon 2 gets the alcohol. So I want to use my Grignard, but not for acyl addition. Again, acyl addition would take any alcohol here and make it a tertiary alcohol. This secondary carbon would become tertiary. Acyl addition is not going to be useful in keeping this a secondary carbon. Well, if I need to make a carbon-carbon bond and I need to have an alcohol, that's a really great setup for an epoxide. Similar to what we saw earlier where the cyanide attacked, I added a new bond at a position adjacent to the alcohol forming. I add a new bond at the position adjacent to where the alcohol forms. Let's see if I can work this one backwards. I want my starting material, or excuse me, my last precursor before this to be an epoxide. And I want that epoxide to be attacked on the less substituted position, carbon 3. If that less substituted position gets attacked by a nucleophile, then the alcohol will form on position 2, which is exactly where I want it. So what is the nature of the nucleophile I want to add? One, it needs to be basic. Good. Grignards are basic by nature. I need it to be basic so that it attacks at the less substituted side. And I need the Grignard to have carbons 4 and 5, where carbon 4 attacks. So first, I'll introduce my Grignard. Notice that this is actually not a Grignard, it's an organolithium, but any organolithium will work exactly the same as any Grignard. And I have to follow this with an aqueous workup. Otherwise, I don't actually get my alcohol. Without step 1 and 2 written in there, you lose points. Because without writing 1 and 2, you're saying that you'll mix this epoxide in a beaker with these reagents. These reagents don't exist together. They neutralize each other. They have to be done sequentially. All right, the question now becomes, how do I get to this epoxide? We know that epoxides can be made using MCPBA and an alkene. I need to make styrene from ethylbenzene. This is going to take more than one step. In my first step, I'll do radical halogenation. This places a bromine selectively on the benzylic position. Notice that this bromine reagent is not using FeBr3. If I used Br2 with FeBr3, I would be running EAS on the aromatic ring. I need Br2 and light, not Br2, not Br2 in water, not Br2 in peroxide, Br2 and light to do radical halogenation of the alkane. Then I need to run a simple elimination. One of the best reagents for running elimination is tert butoxide. Again, this is one of our OChem 1 reactions. Epoxidation we just reviewed in alcohols and epoxides, and radical halogenation we reviewed in section 15 with benzene. This uses section 15 OChem 1, section 18, and section 17 reactions. All right, pause now. Try to see how you might complete the next reaction. The transformation that I see in this reaction is taking a secondary alcohol to a tertiary alcohol. There's a lot of things that I can do with alcohols. For instance, I can run elimination, although not on this carbon, because there's no beta hydrogen to eliminate. I could run substitution, but why would I want to turn the alcohol into something else if I want to keep the alcohol in the final product? I can run oxidation. Oxidation takes this secondary alcohol to a ketone. A ketone is a good precursor to a tertiary alcohol. So to brainstorm for this reaction, I can oxidize to a secondary alcohol. Excuse me. I can oxidize to a ketone from the secondary alcohol, and ketones can do acyl addition to tertiary alcohols. So I'm considering ways I can react with alcohols and ways that I can make alcohols. Synthesis of alcohols, reactions with alcohols. Notice that in your notes, this is exactly how I've organized them. There's a lot of reagents that can oxidize secondary alcohols, and here I specifically have a benzylic alcohol, which means MnO2, PCC, and chromic acid can work here as my oxidizing agents. I'm going to abbreviate those aromatic rings because I can see they don't actually play a role yet. They're not changing anything about the chemistry. From this ketone, I need to make a tertiary alcohol. That can be done by acyl addition. I just need to add the right reagent. In this case, my carbonyl carbon is the tertiary alcohol, and I need to add this group, a benzene ring. That's as easy as adding phenyl Grignard, PHMgBr. This has to be followed with an aqueous workup in order to protonate and form the final alcohol. And here I have triphenyl methanol. I actually want to take a step back and show you how some reactions can be done in multiple different ways. For instance, the last reaction we did, I did radical halogenation, elimination, epoxidation, and epoxide ring opening in basic conditions to get the final product. It's not the only way to do this. Let's say that I had oxidized my starting material to create benzoic acid. This is a section 15 reaction, benzylic oxidation. I then could have reduced my carboxylic acid all the way down to an alcohol. This alcohol can then be oxidized with a mild oxidizing agent into benzaldehyde. PCC takes this benzyl alcohol into benzaldehyde. Now I have a primary carbonyl that feeds into a secondary alcohol. This can be made by acyl addition. First, I need to recognize that I've lobbed off some of my carbons. So this acyl addition needs to have carbons 3, 4, and 5. And then, of course, followed by an aqueous workup. Oxidation, reduction, oxidation, acyl addition. 1, 2, 3, 4. Radical halogenation, elimination, epoxidation, opening. 1, 2, 3, 4. Same number of steps, incredibly different routes, different intermediates, different reagents, both equally effective. Let's see how we can take this benzene ring and turn it into phenyl acetate. We need to make the ester linkage connect from the oxygen and make an ester as our final product. Pause now to see how you might do this. Count your carbons, brainstorm, work forward and backwards. We haven't seen a lot of reactions yet that synthesize esters, but there is one of them in this section with alcohols. That is the acid-catalyzed esterification. Starting materials are alcohol plus carboxylic acid in acidic conditions. Okay, I need to make an ester, and the alcohol portion is always the ester linkage. That means that a precursor I will need here is phenol. I need to have this benzene ring attached directly to an alcohol. I know how to make phenol. We learned how to do this in section 16. It requires NAS reactions. NAS with hydroxide. NAS reactions require a good leaving group. That means having some sort of aryl halide that can be eliminated. How do I make an aryl halide from benzene? That is an EAS reaction. I have two choices based on the reactions we learned about in class, and that would be either bromination or chlorination. Cl2 with AlCl3, or Br2 with FeBr3. Once I have my aryl halide, I can expose this to sodium hydroxide, and I can run the NAS reaction to make phenol. Once I have phenol, I need to introduce a carboxylic acid with acid in order to make an ester. Here is the acid that I need. If you want to draw it in the same shape, then it looks like this, and we need an acid, H+ generically, that will run this esterification. There we have it. Section 16, EAS, NAS, Section 17, acid-catalyzed esterification. Let's run on to this next one. Pause to see how you might solve this on your own. One thing that stands out to me in this synthesis is that the carboxylic acid never changes, but the ketone not only leaves, but the carbon of the ketone transitions into one of the carbons of an alkene. We've seen how to make alkenes by elimination, and there's a couple kinds of elimination that we can run. We can run elimination of alcohols, as we reviewed in section 17. We can also run elimination of alkyl halides, as we reviewed in Unit 1. So if I can run elimination of alcohols or alkyl halides, I want to consider which of them is easier to make from my ketone. We learned in Unit 3 that ketones can be reduced down into alcohols. So if I can take a ketone and reduce it to an alcohol, then I can run elimination. Pause again if you want to try connecting the dots here to go from this starting material to this product using these brainstormed reactions. Well, reduction that leaves a carboxylic acid alone but reduces a ketone, it's very similar to the problem that we saw here. Selective reduction. My mild reducing agent, sodium borohydride, will effectively transform the ketone into a secondary alcohol, and it will not touch the carboxylic acid. Now that I have an alcohol, I can run acid-catalyzed dehydration. Notice that acid-catalyzed dehydration is regioselective. It prefers to go to the more substituted region, and that's exactly the alkene that we get here. Last one. We start with a vicinal diol. Go back and look in your notes for reactions with vicinal diols. And we end with this long chain. If we're mapping our carbons, I want to consider how these carbons might end up here. And I have a suspicion that the carbons that have functionality in the starting material are the carbons that have functionality in the product. And live in front of you, I'm recognizing that there is a typo in this. This structure is not correct. We'll see that once we actually map these carbons out. I apologize for that. 6 carbons from alcohol to alcohol. But here, I've only given you 5 carbons. So this structure is supposed to look like this. This would be a much more challenging synthesis if it did not have the right number of carbons. It is a more challenging synthesis, but it's not necessarily impossible. But I would rather this be what you try to solve for. Mapping my carbons, I'm guessing that carbons 1 and 6 in the starting material are these carbons 1 and 6 in the product. It feels like a good guess because carbons 2 through 5 don't have anything else going on in the starting material or the product. So I need to find a way to cleave the carbon 1 and 6 bond, and I need to find a way to retain some of that chemistry that they have, their bonds to their oxygen. When thinking about cleavage, there's an OChem1 reaction that we learned, oxidative cleavage. So this could be something like O3 with DMS or H2O2, reductive ozonolysis or oxidative ozonolysis. Except that this works with alkenes. And we don't have an alkene here. And to make an alkene would be challenging because I have 2 alcohols. Running elimination won't necessarily favor the production of just an alkene. So ozonolysis doesn't seem great. If you go back and review the reactions with alcohols, we actually saw that vicinal diols go through oxidative cleavage with periodic acid. Or if you're not careful, periodic acid. Periodic acid will take the starting material and it will cleave the carbon-carbon bond, but it will turn carbons 1 and 2 into aldehydes. Excuse me. It'll turn carbons 1 and 6 into aldehydes. I have done something. I've cleaved the 1 to 6 bond, and I've retained the C to O bonds. But I haven't retained alcohols at these positions. The last step in solving this is reducing my aldehydes into these primary alcohols. This can be done with LAH, or it can be done with sodium borohydride. Sodium borohydride is strong enough to reduce aldehydes. LAH is also strong enough to reduce aldehydes. So there we go, a two-step synthesis.